Alright, so last time we touched upon the broader landscape of energy-based models, their potential limitations, and where they might be headed. Now, let's really dig into the nitty-gritty. How do we actually use these things to make predictions? And how do we teach them in the first place? It's a bit different from your standard feed-forward network, right? Okay, first big question. If I have an input X, how do I get a prediction Y hat out of an EBM? With a regular neural network, you just feed X in and, boom, Y hat comes out. But with an EBM, it's not quite that direct. Think of it kind of like how diffusion models work. You start with a random guess for Y hat, maybe pure noise. Then, you feed both your input X and this random guess Y hat into the EBM model. The model spits out a single number, the energy. This energy tells you how compatible this particular pair X-Y hat is. Lower energy means a better match, higher energy means a worse match. Now, here's the clever part. Because the whole thing is differentiable, we can calculate the gradient of this energy with respect to our prediction Y hat. This gradient is like a compass needle pointing downhill on the energy landscape. So, we take our current guess Y hat and we nudge it in the direction opposite to the gradient, using gradient descent. We repeat this process step by step, refining our guess Y hat until we hopefully land on a low energy state, which corresponds to a good prediction. It's like sculpting a statue, but instead of chiseling away, you're nudging the clay towards a desired shape based on a compatibility score. And yes, this iterative optimization process is deeply connected to diffusion models, which are essentially predicting the gradient of this energy landscape to denoise data. So, how do we train these EBMs? Normally, we train models on pairs of data, like images X and their labels Y. But an EBM needs to learn how compatible X is with any possible Y hat, not just the one true Y. How do we handle that? Well, there are basically two main schools of thought here. First, there are contrastive approaches. This is probably the most intuitive way to think about it, similar to how GANs work with discriminators. The idea is simple. We want the EBM to give low energy to pairs that are actually in our dataset, the positive samples, and high energy to pairs that are not, the negative samples. The tricky part is finding those negative samples. You could try generating them randomly, but that's often inefficient. Or you could use a generator like in GANs or run some kind of optimization like MCMC for a bit. But here's the catch. As your data gets more complex and higher dimensional, finding good negative samples becomes incredibly hard, and these methods don't scale well. That's where the second approach comes in, regularizing approaches. Instead of explicitly contrasting positive and negative samples, we train the EBM to perform the optimization task we talked about earlier during training. We start with a random guess for Y hat and show the model the true Y. The EBM learns to guide its prediction from the random guess towards the correct Y. By doing this repeatedly, the energy landscape gets shaped such that the true data points naturally lie in valleys of low energy, while other regions are pushed up to higher energy. It's like teaching the model to find the right answer by showing it how to get there from a starting point. This process is somewhat analogous to denoising score matching, which you might know from diffusion models. Now, let's clarify something important. When we talk about EBMs, we're not always talking about the same thing. There are two main flavors. First, we have explicit EBMs. These are the straightforward ones. The neural network itself directly outputs the energy value E theta of X and Y. The entire job of the network is to learn this function that maps inputs to a single scalar energy. Simple, right? Then, there are implicit EBMs. Here, the energy function isn't what the model directly learns. Instead, the model learns something else, and the energy function is defined indirectly through that learned thing. A classic example is diffusion models. Remember how they predict the gradient of the energy function? Well, the score network S theta of X and T that they learn implicitly defines the energy landscape via integration. The energy E of X and T is related to the integral of the score function. Other examples of implicit EBMs include older models like Hopfield networks, certain types of RNNs, and Boltzmann machines. So, when you hear EBM, it's useful to know whether it's an explicit model learning the energy directly or an implicit one where the energy is derived from something else. Let's tackle some common questions people have about EBMs. First, what is this energy thing anyway? Is it magic? Not really. Think of it as a compatibility score. The model learns to assign a low energy value to pairs X and Y that are good matches and a high energy value to pairs that are bad matches. It's a measure of how well Y fits with X according to the model's learned knowledge. How does it learn this? Well, that's what we discussed earlier with the contrastive or regularizing training methods. Now, how does energy relate to probability? The connection is mathematical. The probability p theta of x and y is proportional to the exponential of negative energy, e to the power of negative e theta of x and y. This means lower energy directly translates to higher probability. Essentially, the energy function is like the unnormalized negative log likelihood. The term compatibility is just a helpful way to think about it intuitively. Okay, more questions. Does training EBMs require calculating the full Hessian matrix, which is notoriously expensive? Thankfully, no. The methods described here only need Hessian vector products. This makes the training cost only about 1.66 times more expensive than a standard feed-forward model for a single optimization step, assuming everything else is equal. That's a relief. Why is low energy considered good, and why don't we just work with probabilities directly? Well, the exponential relationship p theta is proportional to e to the power of negative e theta, means low energy naturally corresponds to high probability. The reason we often prefer working with energy instead of normalized probabilities is practicality. Calculating the exact probability requires normalizing over all possible y values, which involves computing the partition function z theta. This is incredibly difficult in high-dimensional spaces, which is where EBMs shine. By focusing on the energy, we sidestep this normalization problem. And is it okay that the energy scores aren't probabilities? Absolutely. For most tasks, we don't need the exact probability of a sample, we just need to compare the relative likelihood of different samples. Think about reward models used in reinforcement learning. They essentially act like EBMs, assigning a score to actions. What matters is which action has a higher reward relative to others, not the absolute value of the reward. Relative comparison is key. One last FAQ point. Is it okay to train EBMs without using maximum likelihood estimation, MLE? You might think, wait, MLE is the gold standard for training probabilistic models. But surprisingly, for EBMs, the answer is often yes. Why? Because real-world data is often concentrated on a very thin, high-dimensional manifold. Imagine trying to describe the surface of a balloon in a vast room. The balloon is the data manifold, and the rest of the room is outside. If you tried to force an EBM to perfectly match the probability distribution using MLE, it would assign zero probability to anything outside the balloon. This means infinite energy, which makes the gradient undefined and the energy landscape impossible to navigate. It's like trying to climb a cliff face with no footholds. So, instead of forcing perfect MLE, we allow the energy to be finite everywhere, making the optimization process tractable and the model usable. Okay, let's switch gears to the practicalities of training these things, specifically focusing on energy-based transformers or EBTs. EBMs, especially when scaled up, can be notoriously unstable during training. So, how do we make them behave? One crucial factor is the step size, denoted as alpha. This is the learning rate used when we perform the gradient descent steps to update our prediction y hat. We found that tuning alpha is absolutely critical. For the simpler SON models, we even make alpha itself a learnable parameter. Its learning rate is controlled separately. Why is this important? Because alpha directly scales the magnitude of the gradient updates. If you use a small alpha, the effective gradient gets amplified. If you use a large alpha, it gets dampened. This means the optimal alpha value depends heavily on the type of data you're working with. Video data needs much larger alpha values than text data, for example. Interestingly, we also found that using a relatively high optimization step size was necessary for stability. Without it, the gradients tended to blow up. Also, a small detail, we don't apply weight decay to this step size parameter. It's a delicate balancing act. Beyond the step size, architecture choices also play a huge role in stability. For autoregressive models like language models, we found that simply adding a learnable step embedding to the input sequence dramatically helped, especially for the SOAN models. This embedding essentially tells the model which step of the optimization process we're currently at. It seems to help the attention mechanisms work better and create smoother energy landscapes. We tried other fancy things like adaptive layer normalization from D, but the simple time step embedding proved more effective. Interestingly, sticking to the standard Lamotwo architecture and initialization RMS norm, Xavier Waits, Swiglu, Rope turned out to be the best performer. Now, for the more complex STU models designed for System 2 thinking, we found a few key hyperparameters. Using fewer optimization steps generally led to more stable training, as longer chains of gradients can become unstable. Also, how you randomize the step size alpha is super important. If you use the same alpha for every sample in a batch, you get convergence issues likely due to high variance in gradients. But if you randomize alpha differently for each sample and each batch, the training becomes much smoother. We even wondered if randomizing the number of optimization steps might help reduce gradient variance, though we didn't test it extensively. 2 more quick tips for stability. First, we found that clamping the gradients used for updating the predictions could help stabilize training, although it might slightly slow down convergence. We didn't use this in our main experiments because other hyperparameter adjustments were enough, but it's a potential trick to keep in mind. Second, and this is absolutely crucial, normalizing your input data. We saw this firsthand in our NLP experiments. When we trained models without normalizing the probability distributions, the training went haywire, with extreme activations and massive loss spikes. However, when we normalized the distributions, for example by applying softmax, the training became rock solid. So, always remember to normalize your inputs, especially when dealing with distributions or embeddings. So, how do you actually go about training your own EBT? Hyperparameters are incredibly sensitive here, so we recommend a specific order. Start with the simplest variant, SOAN EBTs. These are generally easier to get stable. Once you have SOAN working, you can gradually move towards the more complex STU settings. For tuning SOAN models, follow this order. First, tune the standard stuff, learning rate, batch size, etc. A large batch size is particularly helpful because the random initialization of predictions introduces noise, and larger batches average this out better. Second, focus on the SOAN-specific parameters, primarily the step size alpha and its learning rate multiplier. We found keeping the multiplier around 3 times the value of alpha works well. Then, tune the number of optimization steps. Third, you can experiment with optional architectural tweaks, like whether to make the step size learnable or try different embedding schemes. The main goal here is to achieve stable training first. Only after that, if you want the more advanced System 2 capabilities, should you consider moving to STU models. Keep an eye on metrics like the magnitude of the gradients. If they spike wildly, that's a warning sign. Also, watch the difference between the initial and final energy after optimization. If it's too large or too small, it might mean your alpha needs adjustment. Let's look at some pseudocode to see how this training looks in practice, focusing on STU models without extra regularization. Listing 1 shows an example for a language model, and Listing 2 adapts it for video modeling. The core idea is similar: initialize predictions randomly, then loop for a number of steps. Inside the loop, you compute the energy, get the gradient, and update the predictions. Now, there are 2 key design decisions highlighted here. First, should you detach the predicted distributions between optimization steps? Detaching means cutting off the gradient flow from previous steps. If you don't detach, the model has more thinking time, allowing gradients to flow back further, but this can lead to longer, potentially unstable gradient chains. If you do detach, it's like resetting the thinking process at each step, which can be more stable but might limit the depth of reasoning. Second, when do you calculate the loss? Do you calculate it at every single step, or only at the very end? Calculating it at every step forces the model to be accurate sooner, while calculating it only at the end allows for more exploration before evaluation. Our findings suggest that for STU models, not detaching and calculating loss only at the last step worked best. Interestingly, for SON models, the opposite combination was more stable. A general guideline: if you're calculating loss only at the final step, you should definitely not detach the predictions between intermediate steps so the gradient can propagate all the way back. Okay, you've successfully trained and SON EBT. Now, how do you unlock its System 2 thinking potential? This is about enabling longer, more deliberate reasoning processes. The recommended approach is to tweak the hyperparameters in a specific order. First, remove any detaching of tensors between optimization steps. This ensures the gradient information flows back through the entire sequence of steps. Second, implement loss truncation, meaning you only calculate the loss at the final step of the optimization process. Third, carefully tune the step size alpha. This is arguably the most critical hyperparameter for EBTs, and importantly, you should not make it learnable here. Fourth, tune the number of optimization steps. You might even consider randomizing the number of steps within a range. Finally, you can add more advanced techniques like a replay buffer to store past experiences, incorporate Langevin dynamics for stochastic optimization, and eventually introduce randomized alpha values. All these advanced techniques need to be tuned together while still being mindful of the earlier parameters, especially alpha. It's a complex interplay. One potential future idea is to randomize the number of optimization steps per sample, similar to how we randomized alpha. Just remember that unlike SON models, which use multiple time steps, STU models operate on the same energy landscape throughout the entire optimization sequence. So, wrapping up, we've seen that energy-based models offer a unique way to model relationships between inputs and outputs by learning a compatibility score. Making predictions involves an iterative optimization process guided by the energy gradient. Training can be done through contrastive methods or by regularizing the energy landscape. Achieving stability and scalability, especially with large models like EBTs, requires careful attention to hyperparameters, including the step size, architectural choices, and decisions about gradient flow and loss calculation. And finally, unlocking the more sophisticated System 2 thinking capabilities involves specific tuning strategies. It's a powerful framework, but definitely needs careful handling.